We're finally ready to conclude this long lecture of product measure and their integration. So if we recall, our goal is to show when is the integral of f on this product space is equal to this iterative integration. You integrate the y or integrate x first and do the other. Okay, so this goes on to this main theorem called the Fubini-Tonelli theorem. So suppose I have two sigma finite measure space, and first of all, let's talk about the Tonelli theorem. So here I mark the desired equality to be the diamond, okay? So Fubini theorem tells you the following. So if you have a non-negative measurable function, okay, so then what you can do is that you integrate you fix an x, you integrate the y out, okay, you get a function from x to the integral of basically the f lower x. We saw that's integrable. Let's call this function g, and you do the same thing for y, okay? So you integrate all the x out, basically you're integrating the f upper y, okay? For each y, you have one of these value, and you call this function h. Then you actually have two measurable functions. And because you have two measurable functions, you can integrate it again with respect to x and y, and what you get is essentially the diamond, okay? The equality will hold. Basically, Tonelli theorem is saying as long as you have non-negative function, then diamond will hold. Of course, here you really need a sigma finite here, okay? So that's a really important condition. And Fubini is telling you something about just any measurable function, so you don't need to be a non-negative function. So Fubini says if you have a f which is inside the L1, okay, if it's integrable, then the fx and fy, if you fix an x and y, you actually get a almost everywhere L1 function on their respective measure space. And this function g and h we just defined earlier, you can also make that definition, and they are actually inside their, again, L1 space. And because they're in their L1 space, we can talk about their integration. And we also have this diamond, okay? This equality still holds when you move from non-negative function to L1 functions, okay? So that's essentially what the theorem says. Okay, so for Fubini, the key is you really need this L1, okay? So now let's prove this theorem. So let's prove the Tonelli theorem first. Well, Tonelli theorem, from last time, we proved a little proposition that basically works for the characteristic functions, okay? So we already proved this for characteristic function chi of E, where E is inside the product sigma algebra, okay? So if you go back to the last video, what we proved is essentially what we have in here. So because everything here is just an integral, and the integral is closed and, well, it's a linear function, so immediately what you know is that if you have something, a simple function, a non-negative simple function, so phi is non-negative, phi is simple, Tonelli theorem also holds for this phi, okay? So still hold for this phi, okay? And now for every non-negative measurable function, so if you have f non-negative and f is measurable, well, how do you do that is, well, the standard trick is that you approximate this f by the sequence of non-negative simple functions. So we show that there exists a phi n, okay, they are simple functions, and phi n are increasing, non-negative, and the phi n is converging to f pointwisely, okay, so here f is from x cross y to non-negatives, okay, so phi n are defined on x times y as well. All right, because of that, well, you can convince yourself the following. So if you look at a fixed x and you look at the phi n of x, that's also a simple function, okay? The easiest way is to show this range is clearly finite, and I ask you to show in your assignment. Simple means the range is finite. Okay, and each of these phi n fixed an x, that's non-negative, and they're increasing. And moreover, the phi n of x is going to converge to f of x, okay, f lower x, okay, you restrict an x, you treat it as a function of y, okay, this is really a function of y. All right, and because of that, you have the MCT, so the integral of these phi n of x, d of nu of y, okay, that's just going to converge to the f of x, d nu of y, okay, f lower x. Again, this is a function of y, this is a function of y, okay. And because you have this convergence, and then you apply the MCT again, so you do another integral, and they still converge, okay, so you can really say you do the other one, okay, so integrate respect to x now, so you still have the same convergence, okay. And because we showed these, when phi is a simple function, this iterative integral is the integral of phi n with respect to the product measure, okay, so this is because phi n is simple, so it's a finite span of these characteristic functions. And because of these phi n is simple increasing converge to f, so by MCT we know it converges to the integral of f under this product measure. So what we can conclude is that this Tonelli theorem will hold for this f, okay? So this proves the Tonelli theorem part. And to see the Fubini part, well, let's fix f inside L1 of this product measure. So let's fix f inside L1. All right, so one thing is because it's in L1, so immediately I know the integral of its absolute value by the definition of L1. Okay, this is just saying that this one is less than infinity. Okay, this is finite. Well, but this one is a non-negative function. Okay, so this is non-negative, so you can apply Tonelli theorem. So by the first part of this theorem, the Tonelli theorem, you know this can be written as an iterative integral, okay? So you can do the f of x, y, you integrate the y first, for example. So let's do mu of y, and then you integrate the mu of x, okay? I realize I didn't really do the other direction. You integrate x first and then y, they're really the same proof, so I'm skipping it. But in any case, so you see that this integral is still finite, okay? So when you're integrating something when you have an integral that's finite, then what you can conclude is that the function you're integrating, so this function, so the x integrating the absolute value respect to d mu of y, that's going to be finite almost everywhere x, okay? This is essentially just integrating the absolute value of the f lower x d mu of y, okay? So in other words, these f lower x is inside L1 of mu almost everywhere, okay, for almost everywhere x, okay, the f lower x is a L1 function, and you do the same thing for y, okay. So now the g of x by our definition is just the integral of these f of x d of nu of y, okay, this is a function of y. And because this is in L1, this integral is well defined, okay? Now I want to show that g itself is in L1 as well, okay? So let's compute integral of g of d, now is the mu of x, g is a function on x, okay? So by definition, this is the integral of the absolute value of these integral f of lower x d mu, okay? And skipping the y here, and then you do the d mu. Okay, and we proved that the absolute value of an integral is less than or equals to the integral of the absolute value. So it's less than or equals to this double integral where you do the absolute value f of x, integrate respect to nu first, and then you integrate respect to mu. Okay, so but this one is less than infinity, okay, because this is the integral of, by Tonelli theorem, this is the integral of the absolute value of f, okay, so mu cross nu, okay. So this proves that g is also in L1, and you do the same for h, okay, h is also in L1. So the integral really makes sense, okay? So the integral of g of x, the mu of x makes sense, okay? So let's say it makes sense. All right, so if you want to, because it makes sense, now if you just want to prove the Fubini theorem, you say, well, f is inside L1, so you can treat f as a difference of the positive part minus the negative part, okay? And you can apply the tonality theorem for the positive and negative part. So the integral of the f positive part, the mu cross mu, that's just going to be the double integral. You integrate respect to y first, so the mu of y, and then you respect to x. Okay, the same thing happens for the minus, and everything here is linear. So you prove this proves the diamond for this function f. Okay, so first of all, both of these integral is less than infinity because the h and g we defined are L1 functions. Once you know they're L1 function, the rest is really simple, okay? Because they're positive and negative part. When you integrate it, still have a finite integral, okay? So everything just follow, all right? So we finished the proof of this tonality and Fubini theorem, okay? So finally, after all these videos, we done with the main result of this lecture. So just want to remark a few things. So Fubini and tonality are just really important theorems. So the first of all I want to remark is the sigma finite is really necessary, especially for the tonality theorem. But it's actually not necessary, but for the so it's optional actually for the Fubini theorem. Okay. So because really in the Fubini theorem, you're requiring your function to be an L1 function, and L1 function is actually supported on the sigma finite set. Okay, so I'll probably put that on your assignment, but basically you don't have to assume the measure is sigma finite. Okay, the function, if it's in L1, then it cannot be too bad. Okay, that's why you don't really, you see, for example, in Ken's course note and a lot of the reference books, the Fubini theorem is stated without the sigma finite assumption. And second, I just want to say that another thing is Fubini and tonality really come together. So in general, if you want to compute something like the integral of f of x d, let's just say d mu, and maybe I should just say the product measure d of mu cross mu, well, if you want to invoke the Fubini theorem, usually the first step is you check this function is integrable. So check f is actually in L1. And to check f is actually in L1, you're really just computing the absolute value of f. Okay, and this usually use the tonality theorem. Okay, so that's we already saw that in our proof of the Fubini theorem, we're kind of already using the tonality theorem, okay? So basically, if you want to use Fubini theorem, usually you have to use tonality theorem anyway, so they really come together, okay? So after you check it in L1, you can now use Fubini, okay?